Welcome everybody, my name is Connor. We've got a lot to get through. We're talking Autonomous today, we're talking Apex because it's just been released on Autonomous, and we're talking SQL. We've only got an hour, so let's get straight into it. And I thought I'd start with something simple. Let's start with a nice picture. That is a background of a Perth sunset. Now, why did I put a Perth sunset? Because it's an excellent background. It's a lovely background picture. I often use it as a backdrop on my machine, and it leads me into a good background in terms of SQL processing. And the reality is, as most of us know, that if you can master SQL and the way SQL is processed, really it's mastering successful application development. And that's what we're going to be targeting today. My name, as I said, is Connor McDonald, and I'm from Perth. And as I'm talking here, I have to make sure that every time I have a picture on the slide that I give it enough time to make its way across the world. I live in Perth. It's on this side of Australia. Obviously, anyone that's on the call that wants to visit Australia, you're more than welcome to visit Perth. I can show you all the site. There's not a lot there in Perth, but you're welcome to visit. Rather than blitzkrieg you with a zillion social media links about LinkedIn, Twitter, etc., etc., I came up with a nice simple version of a thing called Linktree. So linktr.ee/Connor. If you go to that website, it'll have links to all the many ways you can get in touch with me. Twitter, blog, Facebook, Instagram, LinkedIn, etc., etc. Feel free to reach out, and hopefully we can talk tech at some stage in the future. This is what I do most of the day. For those that have not met me or not heard of me before, I look after the asktom.oracle.com website with Chris Saxon. Tom Cart retired in 2015, and so we resurrected the site, and hopefully we answer all your questions. And this is probably the more important one. This started last year. This is our website called asktom.oracle.com/office hours. We realize that there's a whole lot of people inside Oracle, a lot of people smarter than me, that you've never met and probably will never meet because they are inward facing. They don't have the luxury of my job where I get to go meet customers and meet members of the community. They just focus inwards on their tech. So we wanted to make those people available to you at least for an hour a month. That was our aim. So a lot of the people that you would not see at conferences or not see out in the community still make their time available to you for at least 1 hour a month. So, and that includes the Apex team. Members of the Apex team do several of these events per month. So it's a great way of staying in touch with the Apex community, which I know is bread and butter. We've done 200 so far since we started this. But let's get on to the topic at hand. SQL is like any language. You compile it. Now, obviously, SQL you compile on the fly. It's not like a C program or a Pure SQL program where you compile it and the compiler gives you some sort of feedback. From that point, you proceed. You compile it on the fly. You throw it at the database and it processes it for you right there and then. You then run it and then you get and store the results. So it's pretty much like any program. Make sure it's going to work, do the work, and then process the output of that work. So if you're going to build a successful application, obviously what we ideally want to do is be able to compile our SQL fast, run it fast, and get and store the results fast. If we can tick off those 3 boxes, then we've achieved a lot. And that's pretty much it. That's really all we have to worry about. If we can achieve those things, we're good to go. This is what everyone talks about when they talk about SQL performance and SQL processing. I said we compile, we execute, and we store, fetch some results. Just about every talk I've, presented or given or seen or attended in my 25 years plus of working with Oracle is focused on the middle one. How do we execute SQL quickly? So we look at things like the execution plan and whether we have indexes and all those things about running SQL fast. So I think that's pretty much been done to death. And so this session I wanted to focus on the opposite. We're going to spend minimal time, if any. If we run out of time, we'll skip it, on the actual concept of executing the SQL. Because in an autonomous world, a lot of the heavy lifting in terms of how to best run or execute an SQL statement is taken care of. However, it is still the responsibility of the developer to optimize the compilation phase and the storing and executing phase. The autonomous database can't do that for us. The responsibility lies with the developer to do that as efficiently and effectively as possible to make sure our applications run well. We'll be going back to the very core principles of how compiling SQL and how fetching and retrieving results from a SQL statement after it's executed are handled because those fundamentals are going to be critical to writing successful applications. So before we begin, I thought I'd throw in some controversy, and that is, here is the problem with most applications nowadays. And the problem is, it's us. We're the problem. And to help explain why this is sort of a recent development, let's take a little small digression on a small history on database servers, in fact, any servers. Not too long ago, this was the diagram that you would see in most tech books about how computers worked. In fact, when I went to college, I won't reveal exactly what year that was, but it was some time ago, we learned about what we call bus-based computing. And that is, all the components on a server or on a motherboard talk to each other via a bus. FSB in that diagram stood for front-side bus, and that's pretty much how most computers worked. Any access from one component to the other, CPU to memory, CPU to disk, any kind of interaction, had to go along that bus, and therefore the bus was the bottleneck. So as CPU technology evolved, computers actually didn't get a lot faster. CPUs got faster, but we didn't actually get any of the benefits of that evolution because the bus-based computers pretty much were limited by the speed of the bus. This was a great time if we were application developers because there were physical limits on how fast a machine could actually run, and if you needed to do more work than it could do, it wasn't your fault. There was simply a limitation of hardware. The CPU was capped at the speed of the bus. Then it all started to go downhill for us as developers when AMD came along. They introduced this thing called hypertransport, and what they did was, using this diagram, they actually physically bolted the memory right next to the CPU. So each CPU could rapidly get access to a subset of all the memory, but they also introduced incredibly fast links between the CPUs, which weren't limited to bus speeds, to allow incredibly fast computing. AMD pretty much owned the database server market when they introduced this. Anyone that's been in the IT long enough will remember Opteron servers, which we did all our benchmarking on because they were insanely fast. Memory access could be done directly from a CPU. Intel came along and thought, hey, this is a pretty good idea. I wouldn't accuse Intel of stealing anything, but maybe they borrowed some of the ideas and introduced what we call the Nehalem architecture. This is way back in 2007. Same kind of thing. They had this thing called QPI, which was Quick Path Interconnect. The same logic occurs here. Memory attached to the CPU and incredibly fast links between the CPUs. At which point you're thinking, well, why do I care about all this server tech stuff? This doesn't seem related to a SQL talk. Well, the problem is we can't blame the servers anymore. In the good old days, servers simply couldn't do the work. Nowadays, servers can do insane amount of work. And so if you can't get the performance that a server can actually genuinely offer, it's us. It's our fault. It's not the server anymore. So if you're struggling to get the performance you require out of your applications, rest assured, it's not a hardware problem. It's an application coding problem, and that's why we're tackling SQL processing today. It's funny how people debate this with me. They say, well, the world has changed now. We have IoT, Internet of Things. We got mobile phones. We have gobloads of data. All that stuff really, in my view, still doesn't matter. It doesn't mean you have to race out and get Mongo. It doesn't mean you have to race out and get Cassandra. I think that's a lot of fiction. I think we have this knee-jerk reaction, and you see people saying, we won't be able to use Apex because we're moving away from relational databases because our volume of data is so large our relational database can't cope. I think that's fiction. What happens is if a relational database can't cope, it's normally bad coding. It's as simple as that. Don't get me wrong, all those solutions have their place, but at the very, very extreme end of data requirements, nowhere near what most of our applications will ever go near. And one of my favorite quotes is, the sooner you admit that you're not Google, the sooner you can actually get down to doing some real work. So what's holding us back? In particular, the autonomous database offers astounding levels of performance, but we need to make sure that we can obtain those levels with good code. And the things that will prohibit us from doing so are doing too much work to achieve a simple task, for example, compiling SQL, or not being able to do work, having other parts of our application code blocking us from getting stuff done. If we can solve those two things, we can get enormous value out of the autonomous database. So part one of today, I'm going to keep an eye on the time, part one is compiling SQL. And obviously the aim is to compile it fast. And really what this is how to avoid excessive work when processing those SQL statements. So let's do some terminology first so we're all on the same page. We have the concept of what we call a cursor. And let me give you some examples of the kind of commands we run against the database. And the obvious question is, which one of these is a cursor? Now, obviously the one at the bottom left, which actually has the word cursor in the actual piece of PL SQL code there, that's obviously a cursor. The question is, which of the other ones are actually cursors? And internally inside Oracle, they all are. Everything you throw at a database is actually a cursor, even if you don't explicitly have the word cursor in the syntax. A drop table command is a cursor. Anything the database has to run on its server is a cursor, because internally, the definition of a cursor is actually not something to do with actual SQL. It's actually to do with a request to do work on memory on the database server. The three phases that we're familiar with as when we write cursors explicitly in code, and normally we open a cursor, we process or fetch, and then we close it. But inside the database server, really those three phases mean different things. What they mean is, open simply means give me a pointer to some memory, allocate some memory and give me a pointer to it. Process means obviously do some stuff with that memory, and close is here's the memory back. So you can see that anything we do on the Oracle database is actually processing a cursor. Since we're allocating memory, it means we have to have access to that memory, or have to control that access to the memory, because lots of people are accessing memory at the same time. That's the measure of a successful database. Let's do a quick primer on database memory. This is a diagram I stole from one of my old university textbooks, one of those lessons I probably should have listened a lot harder in, and that is how memory structures are mapped in various ways. We have queues and stacks and all those kind of things that we learned in college or at initial programming courses, and almost all Oracle memory looks like this. It's a doubly linked list. You can basically traverse it left to right, or you can traverse it right to left. That's why, funny enough, when people went from 32-bit to 64-bit database, they had to buy more memory, not because they needed more SGA, because they needed more size for all of those pointers. All the pointers went from 4 bytes to 8 bytes for 64-bit. So the vast majority of Oracle memory is linked lists with in both directions. So in terms of controlling access to that memory, I'm going to come up with a metaphor now which hopefully takes some of the technical elements out of it and hopefully makes it very clear as to why memory access is such a critical thing in the Oracle database. Most of us at some stage, maybe when I was younger, but for those who are younger on the call, you probably regularly go to the occasional concert. And concerts are great. You get to hear your favorite band, you get to hang out with your mates, have a few beers, etc. But there's one problem that everyone faces when they go to a concert: the available toilets. There's never enough. And it doesn't matter what it is, whether it's a concert, whether it's a user group meeting, whether it's any kind of event where we have lots of people congregating. The biggest challenge is being able to get to one of these when you really need it. Behind each door lies a complicated resource, something that actually requires some complexity. And one of the things that's obviously critical when using a public facility is you want to have exclusive access to it. Things get really awkward if you have multiple people accessing the same resource at the same time. I actually took this photo with a little bit of picture editing when I was at the Kscope conference. And yeah, you get some interesting looks from the cleaning lady while you're trying to do this. But I digress. But it is true that effectively at a public event, when you're trying to use the facilities, it's a limited resource. Lots of people are competing for it. Concurrent access is going to cause problems. And behind the door, it masks a complex system. And it actually is the same with memory. Now, how do we control public toilets? It's a complex system. What we do is we put something very simple and very known to everyone in front, protecting it. We simply put a little lock like that, or generally it's just a little latch. And it literally is the same with Oracle memory. We actually have these things called latches. If I have two people, and I've represented that here, or two server processors represented by the two laptops here, trying to compete for a similar piece of memory, that's the doubly linked list you can see there in pink, what happens is those structures are protected by a lightweight piece of memory, much like the latch in front of a public toilet door. So what happens is when people want to get access to the memory itself, the first thing they have to do is get the latch. So the little server process on the left, he gets the latch, he takes the lock out just like a person would, Now that they have exclusive access to the resource, the memory, they can then access the memory, and you can see how that's equivalent to the complex resource behind the facility door, make any changes they need to do, but also it might just be reading. Even reading might require exclusive access because you've got to stop other people from changing it at the same time. When you're done, then you release the latch, and then effectively you have freed up that resource for other people to use. So I suppose one of the takeaways from today's session is that yes, Oracle memory is much like a public toilet, but please don't quote me on that. But just like the public toilet, if you have contention, if you have a lot of people competing for a limited resource, then you have some problems. Latch contention means someone has to wait. And that's the example there where we have two people at the same time going for the same latch in order to access a piece of memory. And I note there that just because you're accessing the same latch doesn't necessarily mean you're competing for the same memory. In the example there you can see on screen, it could be the server process on the left wanting the first piece of memory, the very leftmost pink box, and the person on the right might want the very rightmost. But because those memory structures are protected by the common latch, sometimes we actually have this what we call false contention. The key thing here is it's an active wait. It's much like going to the toilet and just smashing on the door continuously saying, when are you going to be out? The database does the same thing. It's too expensive or too slow for the database to try get a latch and then say, yep, okay, I'll relinquish my hold on the CPU and wait for the server to come around and schedule me again. That's way too long because latch acquisition is incredibly brief and incredibly fast. You know how fast it is to access RAM. It's measured in nanoseconds. So we do what's called spinning. And what the server process does is something that looks like this as it hopefully makes its way along the screen. It literally burns CPU going, try get that latch. Oh, someone else has got it. Try again. Someone else has got it. Try again. And just continually, just aggressively goes and goes and goes. So it actually uses a lot of CPU to actually try acquire a latch if someone else has got it. And this is what effectively becomes observed. Your server is going up in smoke. It's burning CPU very, very hard. Now, obviously, with the autonomous database, you can choose as many CPUs as you like. You can scale to ridiculous extremes. But obviously, it's far more intelligent to be using that CPU to get work done, as opposed to sitting there spinning your wheels, burning latches because you aren't using the database intelligently. And here's the key thing. Latch contention hurts CPU. It hurts concurrency because if one person has a latch, no one else can acquire it. And here's the key thing, is you're really, really working your server hard to achieve nothing, to get nothing done, because that's what latch contention is, other people not being able to do work. If you want an idea of how important it is to Oracle, just jump onto My Oracle Support and do a search for the word latch or mutex, and you'll see some of the incredible advancements we've made in terms of the underlying technology from the older versions of Oracle up to the current versions of Oracle. It's critically important that we get latch acquisition as fast and efficient as possible, and that's why with each upgrade of the database, the concept of latching gets more complicated but also more efficient to try and minimize the overhead and maximize the benefits of the incredible CPU power you get on some of the modern servers that we run Oracle on. We're 20 minutes in, you're going, geez, I've given me a history of servers, a history of memory, a history of latch contention. Wasn't this meant to be a SQL talk? Well, to run a SQL statement, you have to do a lot of things, and this is the compiling SQL part of part one. And we can think of it literally in 6 parts. Quick sip of water. Those 6 parts are, the first thing when an SQL comes along is we need to check syntax. And what syntax does is, will this SQL be possibly valid on any database? And you can see there the example select star from emp, and I spelt from wrong. It doesn't matter what database I'm on that runs SQL, any Oracle database, and in fact any database that runs SQL, that will never work. That's what we call the syntax phase. Is it syntactically correct? After syntax comes validity, and that is an SQL may be valid, an SQL may be syntactically correct, but that doesn't necessarily mean it will run on a given database. In this case, I'm doing select emp n00 from emp. Now, that is syntactically valid SQL. It is potentially valid depending on the database structures I have. It's invalid because I've specified the wrong column name. I put the extra O there for employee number. So that's the subtle difference between syntax checking, is it potentially correct SQL, versus validity, which is I now look at the actual database structures inside the database to see if it actually is valid. After that comes optimization. My SQL is syntactically correct, it's valid on this database. Now, what's the best way to run it? And that's what we call the optimization phase. That actually is like the execution plan. That then becomes what we call row sourcing. And it's really sort of a variation on a theme here. What row sourcing is turning the optimization, the execution plan, into a list of instructions that the database will follow. This is the index I'll use, this is how I'll navigate my way down the index, this is how I'll access the table blocks, etc. So you could think of it as the physical manifestation of the optimization plan. And then we finally get to run the thing. We take those instructions and actually perform the work. And the final stage, if it's a select statement, would be fetching those results. Obviously, if it's a delete or an update, a delete, an insert, or an update, then we don't have to fetch unless there's a returning clause. But most of the time, if it's select statements, then that's the last and sixth phase, the fetch phase. There's a lot of preliminaries there, a lot of stuff going on before we actually got to run the thing. Syntax, validity, optimization, row sourcing, and that's what we call parsing. That's the compilation phase of a SQL statement. As you can imagine, there's a lot of memory access going on there. And hopefully this is the light bulb moment where you're thinking, oh, maybe all that memory access about latching is about to become relevant here. And it's true. Think about what you would have to do if you had to work out whether an SQL could run on your system and the best way of running it. You need to look up all the variations of SQL statements that are available. You need to look up all the columns, all the tables, all the grants. Is this SQL statement pointing to a synonym, which points to a view, which might point to a table across a database link? There are literally hundreds of things you may need to access, all the definitions of which will be in memory. And you have to access memory, then you have to protect that access with latches. Now you might be thinking that's impossible to avoid, and that's why we invented this thing called the library cache. And I'm hoping that this is old news, but if not, we'll touch a bit of revision here. The library cache in Oracle simply records all the previously executed statements. So I'll parse a statement like this, and parsing it will compile it and use a lot of memory access and a lot of latches. But then what I'll do is the next time I see that SQL, I'll remember all that work I've done. So if I see that again in the library cache, then I know by definition, syntactically and semantically, the validity checks, they're already done. Because if the SQL is in the library cache and it's been run once correctly, then it's going to be correct again. And I also don't have to work out the optimizer information because I've stored that in memory as well. So the first parse did a lot of work, but all the others managed to benefit from that work that first person did. And then we can reuse all those things. It's pretty cool. So here's an example of a whole stack of different SQLs that have been fired at the database. And there's my library cache. So the first one goes in, the second one goes in, and as it fills up, we get to see that as we repeat the same SQL statement, then we manage to bypass 2 full parsers. And that's a good thing because a full parse is lots of memory access, lots of latches, lots of CPU. Now you might be thinking, well, the probability of reuse seems pretty low in this case because obviously most SQLs are going to be different. And the way we resolve this is what we have in this concept of nearly the same. Some queries are nearly the same. If I look at those 2 queries on screen, I can see that really they're both probably a primary key lookup. The only thing that's different is the value of the employee number. Looking at them purely in terms of character analysis, they are different SQLs, but I could make some assumptions that roughly the queries are the same. I'm getting the same columns from the same table for a primary key lookup. And that's where the concept of what we call binding comes in. Binding is if I know that SQLs will be the same except for the literal values that make up some of the, for example, the predicates or anything in the SQL, I can say to the optimizer or the parser, parse this without actually knowing the value. I can say parse that SQL knowing that any value I give you is going to be a representative value of every value I could possibly give you. Because once I do that, I parse that, I do some memory work, some latching work, but now I can reuse that work with any value of the employee literal. Now, if I was to do that and replace, Now if I was to repeat that same exercise with that list of SQLs we had before to see how they would go in the library cache, once I've removed the differences due to literals, now I'm avoiding 5 full parses. And so you can see the benefit there of binding. We should reduce the number of parsing we're doing. At this point, this is all hand waving by me and sort of showing pretty pictures on the screen. Let's look at a demo of this to actually see what the actual true benefit is. Now I'm going to show some sample code in Java. And the reason for that is I do this demo at developer events around the world, including Oracle code, and most developers are very familiar with Java as a language. But we can see that even if you're not a Java programmer, the syntax here is very easy to follow. You can see underlined here what the two queries will look like. The first one is I'm simply querying a table from my parse demo, and I'm going to concatenate the string. So that will be a literal on that SQL statement. So it'll be where pk equals 1, equals 2, equals 3, etc. And if we look at the very top of the screen, you can see I'm going to be looping from 1 to 10,000. So I'm going to do 10,000 different SQLs, each one simply with a different literal. The second one is using what we call binding. I tell the database I want you to parse the select from parse demo where the primary key equals a question mark, and then what I will simply do is after I've parsed it once, I'll execute that query 10,000 times, reusing the information. Now, because I'm in Perth and my database is in the United States, the latency is going to destroy any kind of attempt to get a true cost of parsing here. So I've showed you sample code in Java, and I'm going to run my routines in Java, but they're just going to call a database resident PL SQL routine to mimic the same amount of work. That eliminates the latency, and then we can actually see the effect of the parsing overhead. So parse demo is doing the 10,000 different SQLs. So each one needs to be parsed. So you can see that's grinding away for a little bit there, but there we go. 10,000 iterations in about 6 seconds. Now that's still reasonably good. We've got obviously a lot of firepower sitting on our autonomous database to crank that workload through. Let's now test the second one, which is where we bind. So we parse the first one and then we reuse the parsing information for all the others. And hopefully that's fairly dramatic. You can see that it is almost 10 times quicker. The cost of parsing often outweighs the actual cost of executing it by a long way. Simple queries, almost all the time, is actually in the parsing element. The response that came back at Oracle Code, and often comes back from people when I do these talks, is, but you just told me I'm doing 1,600 SQLs per second, even in the worst case. Now, that's true, but let's make it real. Who writes queries which are just select from one table where primary key lookup? It's pretty rare. We often don't do it. What we do is we write more complicated SQLs. So I grabbed just a random couple of database objects, all objects in DBA segments, and did some joins. Let's make this a real-life application. So in this case, I'm going to be parsing this particular query and then seeing what it costs to parse that. This is a much more real-life example because this is what SQL looks like when we write it. We have joins, we have predicates, etc. So let's go back to our Java code. This time we'll do Java parse demo 2. Now I'm going to pass an argument here. This is the number of times I'm going to run that complicated SQL we saw on screen a second ago. So I'm only going to run it 10 times. Okay, 2 seconds. Now that's not looking so flash. That means I can only run 5 queries per second on this machine. The moment the queries get complicated, parsing costs go through the roof. It gets incredibly expensive. And obviously that's just not CPU that's being burned, it's latching as well. I'm using a lot of latches, so if other people were trying to do the same thing, they'd be blocked. Which would be sort of a ramp up in CPU where no one gets anything done. And the worst thing is, it doesn't improve with age. If I make it 20, it doesn't scale, it simply blows out linearly. This will take around about 4 seconds. I'm guessing about 4.2, 4.6. So it doesn't matter how many times I run it, I'm literally paying a price that is fixed at about 5 queries per second. Let's replace it now with binding, and I'll do the same. I'll do 20, let's start with 20 for binding. Okay, that's pretty quick. But the best thing is, it scales great. Let's make it 200 times now. So 200 times run binding, and it's actually even faster. And the only reason for that is that first time I've parsed it, it's managed to get into memory. All these subsequent 200 are now not parsing at all. In fact, let's bring it out to 2000. And I'm still 4.2 milliseconds. Let's go 20,000. That's going to be somewhere around about 4 seconds, I reckon. 3 seconds. So as opposed to 5 queries per second, when the query started to get more complicated, now I'm at what? Oh, that's what, 6,000? 6,000 queries per second just to parse. That now is much more of a realistic difference and the massive impact that excessive parsing will have on you. And just in case you're wondering, I'm running on the absolute smallest size autonomous machine I could choose, just a single CPU. And I'm still getting 6,000 queries per second simply because I'm writing code and SQL code and parsing it in a smart fashion. So I hope that convinces you. Even if none of that matters to you, you may have a ridiculously fast server, you may have just a little tiny system where there's only 10 users, you don't care if you can only do 5 queries per second because that might be more than enough. Let's look at something much, much more serious when it comes to using SQL built in that way. If I look at the way I built up that SQL, I simply did it by concatenating strings. If you concatenate strings, sure as night follows day, you're going to get hacked. This is the problem when you build up SQLs. If someone is passing you some information that you're going to use and build up an SQL with, so I'm doing select ename from employee where empno equals, and then someone passed in a parameter. What we're expecting to fill in is something like you can see in the first thing there. We're expecting someone to say, yep, I want employee 6543, and that'll run just fine. But what if they pass in this, the stuff that's in green, 6543 and 1 equals 0, which means the top select will return nothing, union all, select table name from all tables, etc. This is what we call SQL injection. It's the ability of putting values via an input facility that actually end up running as part of your SQL statement. And obviously that might return me, say, a table called security or something, and then of course then I would simply build another SQL. Now that I know I have a table called app security, simply working on that and saying, okay, now I might be able to get the username from the app security table. And here's the thing, obviously that requires some expertise in finding out where you can do this. And that leads me to this picture. This is what everyone thinks is happening when people hack your system. They think it's some guy in a dark room with a hoodie on, and he's probably based in the north of Siberia somewhere. It's all very shady and shifty, and they've obviously got very exotic tools, etc., to actually work out and hack your system. The reality is, this is how you'll get hacked. You're going to get hacked really, really easily. And the number one hacking app that anyone will start with is Google. So I'm going to show you now literally how easy it would be to hack someone. Now, obviously, I'm not sure what it's like around the world where you're joining us, but in Australia, there's this thing called the law where it's actually illegal to go hack someone, funnily enough. So I can't actually show you it for real, but I'll show you some screenshots to give you an idea of literally how trivial it is to hack someone. And as I said, the number one hacking app you would start with is Google. There's a thing what we call is Google dorking. And Google dorking is crafting particular search strings to look for particular information about our website. Not necessarily content, but other things. So you can see there I've typed in that I'm looking for any website that has in its URL PHP ID equals. So I run that search and I get some, let's go forward. And I get some potential results. And as you can see, if you look at the elements in green there on the screen, you can see that these are all examples of sites that they're run by PHP. And it just so happens that obviously somewhere they have an ID flag or field that they can query on. So I've got ID equals 2 in the first one, and etc, etc. So that's all we've searched for. I scrolled down a number of pages and found one and came up with this one. I've blurred out the URL so you don't race off and have some fun with these people. You can see in the URL they've got, I'll zoom in, they've got their URL, then they've got contactus.php ID equals 13. Believe it or not, we are halfway done when it comes to hacking someone's website. how do I know if they're using binding or they're using literals? Well, if they were using binding, it wouldn't matter what I typed in over that 13 because it would be bound and then parsed and then used, and it would run fine. It might, if I typed in 100 million, I'd probably see no results, but the application would work still fine. If that 13 is being used by string concatenation, then if I were to put some gibberish in there, then I would probably break the SQL. And that's exactly what I'm going to do. I then replace the 13 with simply a single quote. And then I hit return on the website and see what pops up. And this came up. You have an error in your SQL syntax. Check the manual that responds to your MySQL server. So straight away I know that this website is using MySQL. And I also know that they're not binding their inputs. They're actually building their SQL via concatenation because the quote obviously has broken some query they've got there. So part one of knowing that the site can be hacked is complete. That immediately, literally by using Google and Google alone, I know that this website is open to SQL injection. Now obviously comes the much more complicated part where I have to work out that list of cryptic things to add to the SQL to work out how to get information from them. Now that all sounds complicated and hard, but it's really actually easy because there are tools to do it. And here's one, for example. It's called Havig, H-A-V-I-G. It's open source, freely downloadable. Any person on the planet can download this. And literally, in the target field at the very top there, I simply type in the URL that I want to go. Now, this isn't the same website, because as I said, I'm not going to break the law by hacking a real website. This is a sample website set up by a security researcher so people can actually test Havig and stuff like that. But what it does is, if we zoom in, the first thing it does, you press go with that URL, and you can see it's going and looking, trying to find things like columns. The very last line says, I'm finding column count. So far it's found 17. If I was showing you this on via video, it would actually show you 17 and 18. It goes through and finds all the bits and pieces it can find about the database underneath simply by constructing very elaborate strings to pass as parameters. So after a while, it comes back and says, there's a list of tables I could find. And you can see there on the left-hand side there, it's got review manager, resource countries, etc., etc. It managed to find all the tables by constructing elaborate parameters to pass on the URL. I then pick a particular table that I'm interested in, and I could actually click Get Columns. And it simply works its way down. For that particular table, now I can do queries against the MySQL, in this case, database dictionary, to find out the columns. I could then, for example, find out that some of the columns on this are email and password. I can simply select those columns and drill even further. I literally click Get Data, and there we go. I've now got some emails and some passwords, and the site is hacked. I've got usernames and passwords, and I'm good to go. That's literally how easy it is to hack someone nowadays the moment you have SQL injection risks. And what that is the moment you build SQL by concatenation, and the most common from that is using literals. So forget about all the performance stuff. That's important, but performance won't put you out of business. If you get hacked nowadays, you are toast as a company. It's the biggest single risk for any organization now is getting hacked, and it takes 5 minutes. I use Google and a piece of free software. That's all it takes to hack a website. In fact, it's not Russian hackers anymore. It's not people living in Siberia with hoodies. These people took out their entire school district. And they didn't even know. They didn't actually do anything malicious. This was in the news. They literally wiped out all their school records because they were just playing and having fun. So it's not, serious industry hackers now that are killing people. It's literally 12-year-old kids having a bit of fun because all the tools you require to hack someone are now fully available. So if you want your SQL to be secure and you want it to be fast, obviously always bind that user input. At this point, you might be thinking, but I'm an Apex developer and I'm using Apex on Autonomous, and Apex is written by Oracle, it runs in the database, so surely all this parsing stuff and the SQL injection stuff, it's not really relevant, and as an Apex developer, this is not an issue for me. But this is what I see when we do security audits for Apex customers, this is one of the most common ones, substitution variables. Because it's easy. It's easier than writing other code. There's some stuff on the screen. I need to search for it, slam it in there, job done. Building SQL with substitution variables is equivalent to building SQL by literal concatenation, because you need to be very, very careful of what people can pass to you. So that's the most common one. Other common ones I see are if people haven't got the appropriate item protection. So people can then put item values in on the URL, and obviously create collection from query, a commonly used API in the Apex collection package, but obviously it takes a string as a query, and people very commonly build that up by literal concatenation. It's super important that you never ever let any kind of user input become part of a SQL statement. And if you absolutely must, try bind it if you can, but if you can't, then you want to be looking at a package called dbms assert, which is a way of checking to see if the value that someone has passed into you isn't full of tricks and trickery to try bypass your validation. So it looks at things like quotes and stuff like that. So look at dbms assert if you absolutely have to, but preferably don't ever build SQL by concatenation or substitution. While we're talking binding, obviously I said we parse the SQL, we found out the library cache, and that's cool. We know that syntactically it must be correct, semantically it must be correct. That actually doesn't mean that we can reuse the optimizer info, because just because an SQL has been seen before doesn't mean it's actually the same. We might have some parsing to do, and it's what we call a soft parse. And a soft parse means I can bypass syntax and validity checking, but I can't bypass optimization, row sourcing, and execution. Why might that occur? Consider something like this. Scott logs on and does select star from employee where empno equals a bind variable. And then Mike logs on and does the same thing. Now, at first glance, it looks like you could definitely get the benefit for Mike of reusing everything that Scott has done. But that might not be the case if Mike has his own table called employee, because that is the same SQL, but it actually points to two different objects. That's what happens when we have what we call a soft parse. We found the SQL in the library cache, but it didn't necessarily mean that we could actually use it for the optimizer information, because we might be referring to a different object, for example. That's what we call a soft parse, that double check to make sure that the SQL coming in is genuinely the same as one we've already seen before. And obviously even soft parsing is better than hard parsing, but it requires memory access, which means it requires latching. Now, can we do better? Recall, a cursor is give me some memory, use the memory, release the memory. Your SQL is always shareable if it's in the library cache, but what happens is the pointer, the cursor is the pointer that points to it. And when you close a cursor, you obviously lose that pointer. What that means is the next person coming in says, oh yes, there's an SQL in the library cache, but they don't have enough information to guarantee that it's actually the same. They've lost the reference to the pointer. And therefore we end up with a soft parsing scenario. Now that sounds like it's impossible to avoid. I mean, that's what all our commands do. We get a pointer, use it, release the pointer. But what if we never actually closed the cursors that we used? Now, that would actually be a bit more complicated, because let's say I've written a program that then has 3 cursors so far. Select from employee, select from department, select from employee with some where clause. I've got 3 cursors. What I'd need to do is, if I come back to running select star from employee again, I could never actually use the open cursor command that we'd normally write in Apex or PL SQL. I would actually have to never close that cursor and actually work out that sort of, instead of my code that would look something like this, select star from employee, it would be, if it's the first time I've ever run select star from employee, then I'll parse it. Then I'll fetch from it, etc. But even when I'm done, I will then say, okay, rather than close the cursor, I'll simply move the fetch handle right back to the start, put in some new bind variables, and run it again. And I need to know that I've at least done it once. So what you do is you don't close the cursor, which hangs onto the memory and all the definitions associated with that cursor. And what happens is, as you build your application, you need to keep a concrete list of every cursor you've ever used, such that you know where to reset them as opposed to closing them. And then you can reuse them. And obviously, if you've got 1 million cursors, you wouldn't want to keep them all there. You'd have to actually throw away some, otherwise you might rat out of memory. And obviously, if someone, say, drops the employee table, then all those cursors that you're currently keeping open, because they point to the employee table, they need to be flushed out because the employee table no longer exists. You've got to make sure that all that's managed. And that sounds really complicated, which is why very few people do it when they're coding. But luckily, there actually is a free solution to do all of that for you. And it's simply this: PL SQL. People often think of the only benefit of PL SQL as being, well, I'm running code on the database server as opposed to in a client application, therefore it's faster. But it's so much more. PL SQL automatically binds, which is cool. Most of us know that. Any PL SQL variable is automatically bound. All static PL SQL is basically automatically uses bind variables. But here's the key things. It automatically holds cursors open as well. So it implements all those benefits I just spoke about and even avoids soft parsing. You get better cursor caching. So what will happen is any SQL in PL SQL, like for example that one there, we use it, it puts it into a cursor cache and keeps the pointer open. So the next time you run that procedure, we won't even have to soft parse. We just know it's already valid. The cool thing is, even if you close it, even if you do open, fetch, and close, PL SQL goes, you know, I don't reckon you know what you're doing, and simply ignores your close request. So even when you explicitly close a cursor, PL SQL will keep that in its cursor cache and hold it open such that the next time you run it, you don't have to have a soft parse. So PL SQL in the database, I'm stressing here, is fantastic for this. Now I put in the database because obviously we can write PL SQL in things like Oracle Forms, we can write it in our Apex code. Because we have to send that across to the database server, it will be soft parsed. That's another great reason for having your code in the database, even if you're running Apex, because you get that benefit of less soft parsing, which means less latching, which means less CPU, which means less money. Part 1 is done. Thankfully, part 2 is a lot faster. Part 3 was the thing about running SQL. I said we'll come back to running SQL. We may skip it because we'll probably run out of time. Obviously, what most applications do is they query database and they put data back in the database. That's what databases are for. And even though Apex runs on the database, it still does the same logical piece of work. It extracts information from tables and puts information back in. Thankfully, Apex is always ahead of the game because it's on the same server, so it has a lot of benefits. But still, there are some things to look at. Let's start with reading data. When you're querying data, you're querying it from the database, and data is stored not in rows in the database, it's stored in what we call blocks or pages in things like SQL Server. So when you read data, you read blocks, and then you extract the rows from those blocks. Now obviously those blocks are stored on disk originally, so that's over here on the right. Because disks are slow, although they're getting faster all the time, we read it into memory, and then it goes to you. So it's from memory to you. But we just spoke. If you're putting things in memory, you've got to maintain the control over that memory, which means lots of things are going on at the same time on the same blocks of memory. And how do we protect memory access? With latching. So when you fetch a row from a single query, just fetch me one row, this is actually what goes on. We have to get a latch to protect that memory. Then we search along a list of blocks in memory where our data will be, read that block, extract the one row we want. We're finished with that memory, release the latch, and give the row back to the client. And if you get lots of rows, which is obviously very, very common every time you do anything inside of Oracle, it's often a cursor loop. We have a lot of latching. So a typical program might look like something like this in Java, but in PL SQL it would be, open cursor, loop, fetch, 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 fetch. To get row 1, we get the latch. We walk along the list. We get the block. We get the row. We release the latch. Give the row back to the client. Row 2, it's the same thing. Get the latch, walk along the list, get the block, get the row, etc. We'll get row 3, etc., etc. And obviously multiple rows are stored in a single block, so there's a very good chance that most of these rows are stored on common blocks. A better strategy is the thing the database implements called pinning. And what pinning is, literally, as the name suggests, is you're literally putting a pin in something saying, I'm interested in this. So you're telling the database, I'm fetching a row, but by the way, I'm going to be fetching a fair few as well. So I'm letting you know that. And what happens is the database, once it's been given that information, can do this. It will get the latch. It will walk along the list, get a block. But rather than just look for that one row, what you'll do is you'll actually put a pin in that block. You actually put a little marker saying, Connor's interested in this one, do not touch it. Now I can release the latch because I know that anyone else that sees that block is going to see that I've got an interest in it and they can't touch it. Because I now have effectively guaranteed access to that block, I can spend a lot of time in that block, a lot of time being nanoseconds, getting all the rows I need from that block. So I got the latch once, I can extract lots and lots of rows. Now that I'm done, I'll get the latch again, take my pin away, and then release the latch. So I get lots of rows for much less latch acquisition. And the only reason the database can do that is because I told it. I said, by the way, I'm going to be hunting for lots of rows here, so please use this pinning option. But of course, how do you say that? How do you convey to the database, I may want many rows? And it's the responsibility of the client. The database can't know in advance, you have to tell it. And this is how it looks in something like, say, Java. You simply say, there's my query. I'm going to do a fetch, but here's the key one. Thing called setting the fetch size. Now, if you're using something like SQL+, you might be familiar with set array size, etc. But the key thing is simply conveying to the database that you want to get multiple rows is critical here. Let's look at a quick demo, but while we've still got some time left. So I'm going to run a fetch demo here where I'm going to fetch a whole stack of rows in batches of 2. Now you might be thinking, why would I choose 2? This is actually the default and the lowest you can do in Oracle. You can't actually fetch one row at a time in Oracle because we need to know if when you've finished fetching that there is no other rows to come. So what happens is even if you say fetch 1 row, the database will actually try fetch 2. The first one is the row you want and then the second fetch to see if there's more to come. So that's actually a mimic of doing 1 row at a time fetches. I can query 500,000 rows in about 10 seconds. Now that's, once again, pretty good. Let's do it in batches of, say, 200. This is me conveying to the database that I'll be spending some time trying to get 200 rows in a single fetch. And you can see, once again, the performance difference is like night and day. In fact, if I crank up to 2,000, let's go 20,000. So yeah, you can see there's a diminishing rule of sort of law of returns here, but still, I can query 500,000 rows in, what's that, a quarter of a second. So that's 2 million rows per second, just with a simple Java program running against the autonomous database. And as I said, I've got it spec'd at the very lowest level, just a single CPU. It is ridiculously fast hardware nowadays. It's incredible. So if you focus on blocks and focusing on round trips, reducing the number of fetches and each fetch getting more and more data, you get dramatic performance benefits. Now there's no such thing as a free lunch. If I have to go to the database and bring back 10,000 rows, then all those rows have to go somewhere and they go into memory. If I actually did a single row fetch like this, just doing 1 row at a time, it took 1:11. I improved it by doing a bulk collect. This is the PL/SQL equivalent of the Java fetch size. That got it down by a factor of 7, down to 8 seconds, down from 1:10. That's awesome. But at the same time, if I look at my session level stats, doing that in this particular example burned up 500 megabytes of memory. I don't care how big your server is. If every single session is burning half a gig of RAM, it won't be long before your server is toast. But as I said, it's a law of diminishing returns. Remember, we're focusing on getting the rows from a block. That's the pinning strategy. So if we only need to pin the number of rows that could potentially be on, say, a single block, which is normally 8K, even doing something like getting them in batches of 100, you can see here it was also a elapsed time of about 8 seconds, so about the same as getting them all in one big giant fetch. But the memory use was only 600 kilobytes. So as a general rule, simply using a batch size of about 100 to 200 is going to get you very, very close to optimal with minimal memory consumption. One of the cool things, as long as you write all your PL/SQL loops in this fashion, for I in cursor name or for I in select statement, implicitly we will convert that to a batch size of 100. Even though it looks like it's just going one row at a time, we're actually getting them in batches of 100. So if you've written code which is open cursor, loop, fetch, 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 close cursor, try ditch that stuff, look at converting them to this format, and you get the implicit batch size of 100 for free. Couple of things to note when it comes to Apex in particular, and this is why upgrading is often a very good option. If you're on any version of Apex less than version 18, all the most common things that query lots of data, classic reports, interactive grids, all do single row fetches to populate the data. Apex is showing its legacy. It's a application that's been written a long time ago. So all those things, single row fetches. If you're on 18 and 19, then classic reports and interactive reports now use array fetches. They've literally rewritten the architecture to actually do batch sizes of 100, which is super cool. Interactive grid does not, but once you're on 19.2 and above, which obviously is coming out soon, then all three will be using array fetches. I specify that because there's been some sites that literally what you could do is you would actually take their applications from previous version of Apex, upgrade them pretty much unchanged to 18, and they get dramatic performance improvements. It's not necessarily visible from the users, but what happens is your server CPU and your server performance goes through the roof. It's fantastic. The final thing we'll talk about, because we've got a couple of minutes left, is the reverse, which is I've got data on my client or in my application. I need to get it into the database. And how do we do it fast? And the cool thing is the same rules apply. Rather than sending in one row at a time, let's try to send it in multiple sets of rows at a time for the same logic. We're trying to do more work with a single trip to the database. As I said, we're thinking in blocks, not rows, when appropriate. Don't get me wrong, if we only need to insert one row, then we only insert one row. But if we need to insert dozens, then think of it doing them all at once. Let's do our last demo because we're almost out of time. Now, I've got to remember, do I need to pass an argument here? No, so I'm going to see how fast I can insert 10,000 rows into a table. And I'm doing it one row at a time. So in this case, I could take 3 seconds. What's that? That's about 3,000 rows per second. Yeah, 3,000 rows per second, one row at a time. That's still obviously pretty good. Let's now do it where we're doing batches of rows. So I'm going to try insert 10,000 rows, but in batches. And I think I hard-coded batches of a couple of hundred in this example. So 3 seconds, 2.2 seconds row at a time, doing it in batches, 32 milliseconds. Let's try and insert 100,000 rows. That's 147. Let's try and insert 1 million rows. Isn't that just insane? It's amazing what you can do if you write the code well to take advantage of the incredible hardware that is available to you. Now we're pretty much at the end of the hour, so I'll wrap it up there. Notice that we haven't actually spoken today about the execution phase at all, and that's the most common thing that people talk about. All we've spoken about is the importance of the bits that surround the execution phase, namely the parsing or the compilation phase of SQL, and then what we do with the SQL after we've executed it, the fetching or the storing of data. They're critical things. The reason I thought it would be worthwhile focusing on these things is I would imagine the execution phase, although at the moment it's critical when it comes to SQL tuning, will, over the years that follow, will become less and less focus of the developer. It'll be the focus of the database engine itself. The autonomous database engine will take a lot of steps to automatically tune SQL for us. That's one of the beautiful things about a database that learns over time. So I think it'll always be the responsibility of the developer to be focusing on how to make sure the parsing is done in the most efficient and secure way, and obviously what to do with their data once it's obtained. Hopefully one day the autonomous database will look after everything to do with execution for us. So if you have some questions or some queries, please reach out to me on Twitter or via the asktom.oracle.com website. But until then, until I hear from you, I hope you enjoyed the hour, and stay tuned. There'll be plenty more Oracle webcasts coming in the near future. Bye for now.